So how many people here have heard of Bayes' theorem? Yeah, that's most of you. Okay, so Bayes' theorem is like a household word these days, right? Which is kind of amazing. What is Bayes' theorem, right? And why is it so important? Well, first of all, Bayes' theorem is something so simple, it's barely worth calling it a theorem. Right? So this is, and the proof of Bayes' theorem is actually so simple that you usually barely even see it. So what is Bayes' theorem and why is it true? And then we'll see why it's important, right? Usually you call something a theorem because it's a combination of it being difficult and being important. In the case of Bayes' theorem, it's not difficult at all, but it's so important that it rises up to the level of being called a theorem. So here's Bayes' theorem. So let's say that H is my hypothesis. And this hypothesis could be something as simple as, I'm a doctor and I'm diagnosing the fact that you have cancer or not, right? So it's just a binary hypothesis. You have cancer or don't have cancer. Or it could be a whole decision tree, right? You give me a bunch of clickstream data, and from that I induce my hypothesis about how people behave, right? What makes you leave my site? What makes you click on this page? What makes you do this and that? Okay? So this is the hypothesis. And D is the data. Okay? And what I want to know is what is the probability of my hypothesis given the data, right? I want the fact that I've seen this data, these measurements or these tests or symptoms or these click streams. I want my hypothesis or my choice of hypothesis to be influenced by the data that I have. And Bayes' theorem is an answer to the question of how do you do that? So here's Bayes' theorem. It says that the probability of the hypothesis given the data is a product of two things divided by a third. The first thing, P of H, is what's called the prior probability of the hypothesis. It's how much you believe in the hypothesis before you even see the data. Like I'm diagnosing, say, people for breast cancer, and I can have a prior probability that somebody has breast cancer before I've even seen them. Right? Before you even walk in my office, I don't know anything about it, so like, 1% of people get breast cancer. That's my prior probability. Okay? It's how much you believe in the hypothesis before you've seen anything. The second term is the probability of the data given the hypothesis. This is, for example, the probability that your test for, say, TB will come out positive given that you do have TB. Okay? If you think of the hypothesis as the cause and the data as the effect of that cause, like for example, you have these symptoms because you have this disease, or there are these words in the document because it's about, sports or something, then what this is really saying is what is the probability that this cause produces these effects, right? What are the chances that you have, a high temperature if you have the flu, right? That's what this is doing. And finally, this term here is just the probability of the data. This is the probability of seeing that data irrespective of which hypothesis is true, right? What is your probability of having, a high temperature, irrespective of, which disease you have or of whether you have any disease at all? Okay. And so Bayes' theorem just says that the probability of the hypothesis given the data is the prior probability of the hypothesis times the probability of the data given the hypothesis, also known as the likelihood, divided by the probability of the data. Okay. So we're going to see an example of this shortly, but first of all, why is this true? And the reason that this is true is actually shockingly simple. It just has to do with the following. You see this P of D here? If you put it over on this side, right, what you get is P of D, right? I can multiply both sides by P of D. This appears from the right-hand side and it appears on the left side. It just says P of D times P of H given D is the same as P of D given H times P of H, right? And if you think about it, these are just two different ways of computing the probability of D and H. The probability that the hypothesis is true and I see this data is the probability that the hypothesis is true and then I see the data given that it's true. Right? This is one option. The other option is that, this is the probability of the data and this is the probability of the hypothesis given the data, right? So these are just two different ways of writing the joint probability of these two things. And Bayes' theorem is just a one-line consequence of that. So Bayes' theorem is really just a restatement of the definition of conditional probability, which you might remember from your Stats 101, all those years ago. Okay? Questions about this so far? why is this important for us? Right? So we're doing machine learning. Let's say we're learning, decision trees. We want to choose a good decision tree. Right? How do we choose what is the best decision tree? Right? This actually, Bayes' theorem gives us a way to decide which decision trees are better and which ones are not so good. Namely, the better decision trees, or the better whatever, are the ones that have the higher posterior probability, hence the name MAP, maximum a posteriori. And that posterior probability is a function of two things. One is how much you believe the hypothesis a priori, and the second one is how well those hypotheses agree with the data. Okay? So let's say that, let's call my most probable hypothesis my HMAP, right? HMAP is the hypothesis that maximizes P of H given D, okay? So argmax H in H means the hypothesis in H that maximizes this expression, okay? So, okay, very good. I want to pick the hypothesis that is most likely considering both my prior beliefs and my data, right? And now let's apply Bayes' theorem to that, right? Which means that I can replace this by this, okay? So all I did from this step to this step was apply Bayes' theorem, okay? And so far I haven't gained anything, right? And now in the next step, P of D has disappeared, right? Why has P of D disappeared? Yeah, exactly. P of D is the same for all the hypotheses, right? It's the probability of the data irrespective of the hypothesis, right? And so it's the same for all the hypotheses and doesn't affect, it's going to affect the value of the MAP, of the posterior probabilities, but it's not going to affect the choice of MAP hypothesis, right? Because it's going to raise or lower them all by the same amount and the winner is still going to be the same, okay? So we get this. And now you might ask the question, okay, so but what was the benefit in going from here to here? Well, the benefit is that it's hard to figure out what this is, directly. Now this has divided things into two pieces. One piece is your prior beliefs, right? You can assign higher prior probabilities to the things that you have some reason to believe are true, right? Usually you have a lot of knowledge about the problem, or hypotheses or assumptions that you're willing to make. This is where you can encode them, right? So in Bayesian methods, this is the new place that you have to put in your knowledge of the domain. It's your prior distribution over the hypothesis. Okay? You could say that some things are completely impossible. You just don't believe that they could happen. Or you could say that some things are possible, but one is twice as likely as the other, and so on and so forth. Okay? For example, you could say that larger decision trees are less likely than smaller ones, because you believe that your phenomenon really is described by a small decision tree. Okay? But turns out we can simplify this even more. We can, let's say, and this is often the case, that we really are lazy, right? As I keep saying, machine learning is great if you're lazy, like me. And like specifying prior probabilities is too much work, right? You have to think too much, right? And we want this all to be automatic. Right, so if you don't want to have to figure out what is a good prior probability for each hypothesis, what can you do? Very simple. You can just assign the same probability to all hypotheses. So like, a priori, I don't care. It's like Monsieur Laplace and whether the sun will rise or not before you've ever seen the light of day. Right? So if you assign the same probability to all hypotheses, i.e. you have a uniform prior distribution over the hypothesis, then this part, right, is also going to be the same for everybody, which means that you can do what? Right, you can drop it just like you dropped P of D, right? And then you just get this. You get that the hypothesis that you should choose is the hypothesis that has the maximum probability of the data given the hypothesis. Also known as the likelihood, right? So the likelihood is the probability of seeing the data as a function of the hypothesis, right? And so now I'm calling this HML, where ML stands for maximum likelihood. Okay? And this is actually what typically study in Stats 101. They study, how to find the maximum likelihood hypothesis, and we're going to see an example of that shortly as a reminder. Okay? So what are the pros and cons of going the maximum likelihood way versus going the Bayesian way? One advantage of going the Bayesian way is that you do have this way to encode knowledge about the domain. Okay? The disadvantage is that you have to do that. And some statisticians really quibble with the notion of you just pulling some numbers out of thin air and saying like, well, I believe that a priori, this hypothesis has a probability of, point whatever, right? The question there is like, well, we're supposed to be looking for an objective answer, and this brings in subjectivity. The Bayesian answer to that is that subjectivity is inevitable. And when you use maximum likelihood, right, apparently there's no subjectivity there, but really you're making the assumption that all hypotheses are equally likely a priori, so that assumption is hidden in there anyway. Okay? So there are these two schools of thought in statistics, the Bayesians and the frequentists. The Bayesians believe in subjective probabilities. The frequentists believe that the only legitimate probabilities are things that are the frequency with which something happens, or the limit of that as you do more and more trials. So for a frequentist, it doesn't necessarily make sense to ask the question, what are the chances that, Mitt Romney will be the next president, right? Well, we don't have 1,000 trials of that to compute how many times, he became president versus how many times Barack Obama won, right? But from a Bayesian point of view, it makes sense to ask that question. Like, if I ask you now, make your best judgment, and you can probably come up with something, okay? So for most of this class, we're going to follow sort of like the Bayesian view of things. But it's good to remember that sometimes when we use a prior probability, it's going to be a prior probability that's computed from data, right? We're going to have a set of documents, and some of them are going to be on sports. There's 10,000 documents, 1,000 of them are on sports, and so my prior probability of sports is 0.1, and nobody disagrees with that, right? Bayesians and frequentists both agree with that. What frequentists disagree with is when I say, well, I think that a priori, simple decision trees are more likely. And then the frequentists will go like, well, but why, where did that come from? Okay. So, I think the right attitude to these things is to not fall into either camp, but to be open-minded and to use the appropriate tool for the job, right? So I think we should look at this as it's one more set of tools that we have to do machine learning with, okay? All right, so let's see a nice example, classic example of Bayes' theorem. All right, we have a patient. And we want to decide if this patient has cancer or not. Okay? So the patient takes a lab test. Right? This is actually literally what happens when you go in. But lab tests are not perfect. Right? If the lab test says that you have cancer, you don't have 100% certainty that you have cancer and vice versa. Okay? So, but let's say that the patient went in and the result was positive, but the test only returns a correct positive result in 98% of the cases where the cancer really is there. Okay? So when the cancer is there, with 98% probability, the test is positive, which means it's a pretty accurate test, but it's still not perfect. Okay? Conversely, let's suppose that the person does not have cancer, then this test, in 97% of those cases, the test correctly comes out negative. Okay? So again, it's pretty accurate, but it's not perfect. And notice that the probabilities are different in the two cases, right? In general, the probabilities of false positives and false negatives are not going to be the same. Okay? Now, there's one more piece of information that we need to have before we can answer the question, what is the probability that the patient has cancer? Right? This is a very typical application of Bayes' theorem, because what we know is the probability of the test being positive given that the patient has cancer, right? We can compute the probability of the effect given the cause. But really what we want to have is the probability of the cause given the effect. Given that this test was positive, what we really want to know is like, what are the chances that this patient has cancer, right? And this is what Bayes' theorem is going to do for us. But for that we need one more very important number, which is the prior probability of cancer in the population, right? A priori, before you even do the test, before you see anything, what are the chances that somebody has cancer? And those mercifully are pretty low. Let's say it's 0.008. Okay. So now let's do this as an exercise. Okay. So what is the probability of cancer? 0.008. Okay. What is the probability of the test coming out negative? Sorry. What is the probability that the patient does not have cancer? 0.992. Correct. What is the probability of the test being positive given that the patient has cancer? 0.98, right? This is the easy part. What is the probability that the test comes out negative given that the patient has cancer?
0.2.
I heard a lot of murmurings, but no clear signal. Be confident.
0.02.
0.02, right? Because they have to add up to 1, right? These two guys have to add up to 1, right? Just like these two guys have to add up to 1, right? So you guys did this one very quickly, right? Sometimes questions are so easy that you start thinking it might be a trick question and you hesitate, right? So here, fear not, there's no trick question here. Although there is an error that people very often make, and we'll talk about that shortly, right? So what is the probability of minus given cancer? So what is the probability that the test comes out negative given, that you don't have cancer?
0.97.
0.97, right? And so what is the probability of the test coming out positive given that the patient does not have cancer? Well, that's 0.03, right? Okay, very good. So now, finally, this is just the data, right? This was just, taking what's in the question and doing, knowing that the sum of, each of these two things has to be 1, okay? So now, what is the probability that the patient has cancer given that the test comes out positive? Okay. Let's write Bayes' theorem. Let's start by writing down Bayes' theorem. Okay, so what do I need to write here? Let me do the first step. It's the prior probability of cancer. I'll just represent it as C, right? Times what? Right. Probability of plus given cancer, right? Divided by what? So probability of plus given cancer, right? Divided by what? Probability of plus, right? That's the only thing left to have here, right? Okay, very good. But what is the probability of plus? It's actually something that we haven't seen how to do yet, right? What is the probability that the patient has cancer? The probability that the patient gets a positive test, irrespective of whether they have cancer or not.
Be the probability they got a plus given that they have cancer times the probability that they have cancer plus the probability of plus given that they don't have cancer times the probability that we don't have cancer.
Yep. Everybody follow that? I can write almost as fast as you can talk. Does everybody agree? Right? So this is a new point, right? So let's parse this, right? We're going to look at this, a little bit more detail shortly, but this is the sum of two things: the probability of plus and cancer, right? Plus the probability of plus and not cancer, right? So let's look at the second one first, right? This one. Obviously, the probability that you have a positive test is the sum of two probabilities. The probability that you have a positive test and cancer, right? And the probability you have a positive test and not cancer, right? Because, that's all that can happen, right? Anything outside of this, is not a positive test. Okay, so everybody agrees with that part, right? Well, so now, using the definition of conditional probability, right? What is the probability of positive and cancer? Well, it's the probability of cancer times the probability of positive given that you have cancer. Okay? So this is the type of thing that we do all the time when we're dealing with Bayes' theorem. Okay? And now at this point, so this thing is equal to this, right? And now we've reduced this to the numbers that we already have, right? P of C we know is 0.008, P of plus given C, right? And now notice that the first part of this is just what we just computed, right? So this P of plus given C, P of C appears in both the denominator, in both the numerator and in the denominator, right? And then the other thing is just the same thing, but with not cancer. Okay? So all you have to do at this point is plug in the numbers. Okay? And I encourage you to do that exercise, but let me actually do something much more fun than plug and chug, which is, give me a guess. What do you think this, looking at these numbers here, right? What is your sense of how likely this person is to have cancer? Just give me your intuitive feeling, your gut feeling, intuition. And do not be afraid to be wrong, right? Because nobody's going to get this exactly right. Yeah.
Like a few percent.
A few percent, like say 5%?
5, yeah.
5%. Okay, so we have one vote for 0.05. Anybody else? So what is your reasoning behind 0.05?
Well, so the prior probability is so low that intuitively you need a very accurate test to get to that, to be able to diagnose that.
Okay, good. Anybody want to say something else, higher or lower? you will get a free extra 10 points in this class's grade if you answer correctly. Now you're really thinking.
1%.
1%. Okay, anybody want to say more?
So isn't this after the test was positive?
Yes, no, absolutely. This is after the test, yes.
Right.
So exactly, notice, right? The test came out positive, right? And you're going to tell this patient, so what you're suggesting, right? And whoever said 1% is doing that even more so, is this person came in, right? They tested positive for cancer. And you're going to tell them, no, don't worry, it's almost certain that you don't have cancer. Are you sure you want to take on that responsibility? What if they die of cancer because of you? Right? This is the decision that, doctors have to make. Right?
Second test.
No, very good. So, exactly. When in doubt, gather more data, right? Do a second, more accurate test if it's justified, right? This is why in TB, for example, we have both the skin test and the X-ray. The skin test is quick and cheap, but if it turns out negative, then maybe you're good. But if it turns out positive, then now you really want to be sure, and that's when you go for the X-ray. So this is a very common thing to do. Okay, so anybody want to throw out a different number, just for the heck of it?
75%.
Okay, 75%. Okay, very good. This is what I like, right? Okay, 20%. Very good. It's getting better and better, right? So
98%.
98%. You score highest for boldness, which may not be for correctness, but okay. So anybody want to say even less than 0.01?
0.05.
0.05. You mean 0.005?
0.05, yeah, sorry.
Okay, very good. I honestly don't remember what the answer is, right? So I'm a totally unbiased, host of this game, right? But let me tell you where roughly the answer is going to lie, right? Anybody else want to fall one way or another and share in the glory of being right, or the shame of being wrong? Except there's no shame in being wrong. Okay.
85%.
Okay, 85. So that's somewhere between these two. Okay.
50%.
Very good, right? We were missing that, old faithful, the principle of indifference, right? So that's the spirit, right? But that's the spirit when you don't have data. And in this case, we do have data. So, okay, but the interesting thing here is, you guys are all over the map, right? So what?
Near 50% is.
You believe near 50%? Okay, so we have 2 votes for near 50%, but somebody here is saying no.
No, it's closer to
Right.
1%.
So, okay, so, for example, he's pretty confident that it's pretty close to 1%. Okay, and the answer is, see, we have this, we have this scale here, and as I said, I don't remember the exact value, but I can tell you, and you just have to plug in the numbers and verify that the right answer is 200%. No, just kidding. The right answer is going to be in the low end of the spectrum. Why is the right answer in the low end of the spectrum? Well, first of all, there was a test, and the test did come out positive, right? So this absolutely has to increase the probability that the patient has cancer, right? Otherwise, the test would be useless, right? So the probability that the probability that the patient has cancer goes up a lot, as a result of the test, right? And when you get this number, you can compare with the prior probability and go like, yes, this really increased a lot. But the thing is that it's starting from such a low basis, right? Remember, the prior probability is 0.008, right? So even if we go with the 0.01, right? This is already an increase, right? I mean, it does increase some, right? It's not going to be 0.008105, right? But here's the thing to remember is that, and this is actually something that people forget all the time. Even trained doctors tend to do this, which is they forget the prior. They just look at the accumulating evidence and say like, oh, now it must be really likely that this person has cancer. And they don't realize that this is the difference between probability and determinism, is that these are just incomplete pieces of evidence. They move the needle, right? But if you're starting from a very low probability, even after moving the needle for a while, you still have a low probability. Okay? So you wind up with a probability that is substantially larger than this, but is much less than 50%. Okay? And again, this is something that happens again and again. Is you have something for which the prior probability, also known as the base rate, is very low. And human beings, for some reason, just tend to not take that into account. And then they make all sorts of judgments that are very off for this reason. In fact, there's a couple of psychologists, Tversky and Kahneman, who actually won the Nobel Prize in economics for having a whole series of studies of how people are, at least apparently rational. And one of the most famous ones is exactly this. You give people a bunch of these judgments, and they get them wrong. So those of you who got this wrong, don't worry, you're in very good company. Most of mankind agrees with you. Okay? On the other hand, it is the case that you can't ignore the base rate. However, just in case the lows are gloating too much at this point, there's a twist to this story, right? Let's say, let's just say for the sake of argument that the probability comes out 0.1. Okay? Does this mean that you can tell this patient to go home happy? Well, it can't be, right? Because if that was the case, then there was no point in doing the test, right? They probably didn't have cancer before the test. That's the prior probability, and they probably still don't have cancer, right? So let's say that the probability went, again, in very, very round numbers from being 0.01 to being 0.1, right? Why is it that 0.1 is something that maybe the patient needs to worry about, whereas 0.01 is not?
Because it's 10 times more.
Indeed, it's 10 times more, so it's a big increase, right? But actually picture yourself, right? You just went into the doctor's office, right? You had a test, and they said you have a 10% probability of having cancer, right? Actually, the good doctors will actually do this for you. They will tell you what the probabilities are, maybe even without the numbers, and they will let you make the decision. And now you have a choice between the following things, right? You are going to go home and not worry about it because, 9/10 probability you don't have cancer. Or, again, this is a very common situation. You are now going to do an invasive procedure. Are they really going to dig into your chest or your leg or whatever and figure out if you have cancer or not, and hopefully if you have it, they'll remove it. Okay, so which one are you going to do? And let's say this invasive procedure, for the sake of argument, something that, you're going to have to go in one day and, it's going to be unpleasant but not too painful, and then you're going to have some recovery period of a week. So what would you do?
Is the invasive procedure going to be sure?
Exactly. Good point. Let's assume for the sake of simplicity that procedure will get rid of your cancer for sure. So there's no uncertainty there, right? So you know that you have a 10% probability of cancer. Do you want to do it? Do you want to do the surgery or not?
It depends on the person, but 10% is enough to scare someone.
Exactly. So both of those things are very true. It depends very much on the person, which is why it should be the person making the decision. But the other thing to
I think it also depends on the cost of the procedure, whether or not it's covered by your insurance. It might be considered experimental.
Absolutely, right? So if it's going to bankrupt you and then you're going to be alive, but dirt poor, you're right. So let's think of precisely. So whether or not you're going to go for the procedure depends on how much it's going to cost in money, how much it's going to cost in pain, how much it's going to cost in time, right? But the reason why you might want to go for it, even with a 10% probability, is that if you have cancer and you don't do the procedure, you die. That's the highest cost you can imagine paying, short of, being tortured all your life or something, right? So this is actually something that we've already alluded to before, but, this is a very, nice case where it shows up, is that what really matters to you is not what is the most likely thing, right? Is what is the outcome that is best for you, given the information that you have. If you really value your life a lot, right, and let's say that the total cost in dollar equivalent of this is $5,000, well, with 10% probability, you waste $5,000, right? Oh, sorry, with 90% probability, you waste $5,000. But with 10% probability, right, you've just saved your life. So if you think your life is worth at least $50,000, you actually want to go with the procedure. And studies show that people tend to value their life at more on the order of millions of dollars. How do people find this out? They ask you questions like, for example, you could get a new job in a different location where you will pay X more, but now you're going to have, a longer commute and an expert increased chance of dying in a car accident. And you can see how much people value their life by, the trade-off between the two. Okay, so the bottom line is, the probability is still low, but it could have put you over the threshold where you decide to go for the procedure. Okay? Hopefully what happens on a good day is that you can do a second better test that is still not too expensive, and then that one will tell you much more surely what's going to happen. Okay? So these are two very important things to keep in mind when dealing with applications of Bayes' theorem, or really decision making in general. One is, do not forget the priors because they can make all the difference. But number two is, you don't just care which outcome is more likely, you care which outcome has the highest expected utility for you. That's actually the technical term, is the highest expected utility. The expected utility of dying is, the minimum you could possibly have, right? And the maximum expected utility is living, a long, happy, and healthy life. Okay? Any questions about this? Okay, so hopefully this example kind of, made everything a little more concrete.